So let's start with this circle, and we will draw a diameter, AD, and F will be a point on that diameter, and that will be the point that we focus on in this proposition. So looking at the line FD, let's say I take this line, and I hold the point F fixed, and I rotate the other end around the circle, starting at D, moving through G, and then C, and then B, and finally to the other end of the diameter at A. Now notice that as I continue cycling this line around the circle, as the line moves closer to D, the line gets smaller, and as the line moves away from D and closer to A, it gets longer. This is the idea that we are wanting to prove in this proposition. If we connect FD, FG, FC, FB, and FA, we want to show that FA is longer than FB, which is longer than FC, which is longer than FG, and FD is the least of all. Another thing we want to prove in this proposition is that given any point on the circle, and connecting that point to F, there will only be one other line from F to the circle that is equal to it. And it will be on the opposite side of the diameter. So let's prove the first part of this proposition. Take E to be the center. And on every point of the circumference we have marked, we will create a triangle. And we do that by connecting EB, EC, and EG. So that we have triangle FEG, triangle FEC, and triangle FEB. Now in triangles, any two sides are longer than the third side. Another point we want to make is that EA, EB, EC, EG, and ED are all equal, because they are all radii of the same circle. Let's first prove that FA is greater than FB. BE plus EF is greater than BF. But since BE is equal to AE, being radii of the same circle, AE plus EF, which is AF, is greater than BF. Now let's prove that BF is greater than CF. BE is equal to CE. Both of these two triangles share EF, but notice that angle BEF is greater than angle CEF. And we know that greater sides correspond to greater angles in triangles, therefore, BF is going to be greater than CF. For the same reason, CF will be greater than GF. Since we have triangle GEF, GF plus EF will be greater than EG. EG is equal to ED, so GF plus FE is greater than ED, and if we subtract EF from both sides, we find that GF is greater than FD. Let's now prove the other part of the proposition, that on any point on the circumference connected to F, there will only be one other line on the circumference connected to F that is equal in length, and it will be on the other side of the diameter. This is pretty apparent from what we have already proven. If I take line FD and hold F fixed, and rotate the line around the circumference, then this line will get longer as I get closer to A. At some point, it will find a spot equal to FG, and then it will become greater. To show that such a spot does exist, we can construct EH such that angle FEH is equal to angle FEG, and then we can connect FH, which gives us another triangle. This triangle shares a base, EF, with triangle FEG. EH is equal to EG. They have two angles that are equal. Therefore, we know that these two triangles are equal, and so FG is equal to FH.